I'm Bob Parks, and I'll be speaking about precision cementing of doublets without using a rotary table. I'd like to begin with a brief outline of the talk. I will review what is meant by lens centering and why it is traditionally performed using a rotary table. Then I will introduce the concept of using a Bessel beam as a reference axis because it simplifies centering and makes it faster. We will show how to make Bessel beams using an axicon grating and a point source of light. Since we will be demonstrating the cementing of a doublet, I will go over the doublet design and the possible lens conjugates that could be used for centering. Then I will show you how to align the hardware for doing the centering, followed by the actual centering and cementing of the two elements. Finally, I show how repeated lenses are centered without having to move any of the hardware. Centering means getting the centers of curvature of lens elements on a common axis, because the optical axis of a lens is the line joining the centers of curvature. Traditionally, precision centering is done on a rotary table. The axis of rotation is a reference axis in space. A feature of an object on the rotary table, such as a center of curvature, lies on the table axis if it remains stationary as the table rotates. This method works well and has been used for decades, so why change? The answer is that the method is complex and the hardware expensive. If centering is done on a stationary platform, it can be done faster, as much as 5 times faster. And since the method is simpler, the operator has a less strenuous job and is more efficient. One alternative reference axis is a linear stage. Unfortunately, linear stages are difficult to make perfectly straight and to get square with orthogonal axes. We demonstrate this lack of straightness by tracking a Bessel beam with a point source microscope as the PSM is moved along a vertical linear stage. The PSM software tracks the spot lateral motion as the stage moves. The outside tips of the crosshair are 30 microns apart to get a feel for scale. This demonstration argues that you do not want to have anything moving when you are doing centering and cementing. Another potential reference axis for centering is a Bessel beam. Bessel beams are easy to create using a point source of light to eliminate a plane grating of equally spaced concentric rings. The diffraction pattern from the grating creates the Bessel beam that travels in a straight line for meters. The core of the Bessel beam is about 7 microns in diameter and is surrounded by a series of equally spaced rings that extend millimeters from the core. It is easy to centroid on the bright core with a digital camera to a fraction of a pixel. We create a Bessel beam using a point source of light, shown to the upper right of the diagram, located near the normal to the center of the grating pattern, the blue line. The grating creates a Bessel beam in transmission, heading downward toward the lower left, the solid red line, on a line joining the point source and the center of the grating pattern. The grating also creates a reflected Bessel beam, mirrored about the normal to the center of the grating, heading to the upper left, the solid red line. As the point source is moved onto the normal to the center of the grating, the reflected and transmitted beams also move onto the normal and are coaxial with each other and the normal. Our grating, with 50 line pairs per millimeter spacing has a first-order diffraction angle of plus or minus 1.82 degrees for 635 nanometer illumination. A microphotograph of the central portion of the bright chrome-on glass grating is shown to the lower right. A point source microscope, or PSM, is used to both illuminate the grating with a point source of light from the focus of the objective and to detect the Bessel beams reflected or transmitted toward the focal plane of the objective. The PSM is a digital version of a classic autostigmatic microscope, an instrument similar to an autocollimator but with a finite focus. In fact, the PSM is an electronic autocollimator if you remove the microscope objective because of the internal infinite conjugate optics. Notice that the point source of the PSM in the diagram, the focus of its objective, and the crosshair on the video camera are all conjugate. This means that light spots centered on the crosshair are conjugate with the point source of illumination or are on the optical axis of the PSM. Autostigmatic microscopes are familiar optical instruments because they are used in almost all optical manufacturing facilities to measure the radii of curvature of test plates and lenses. Here we have the setup for centering and cementing doublets. The PSM is adjusted in height so that its focus is at the center of curvature of the meniscus element of the doublet as it serves on the vacuum chuck that serves as the lens seat. The window serves to protect the axicon grating below it and to act as a portion of the vacuum enclosure to hold the meniscus on the chuck. Notice that when the PSM is at the center of curvature of the upper side of the meniscus, it is not at a conjugate of the meniscus for collimated light coming up from below the lens, because the meniscus has negative power. The next slide shows how the Bessel beam from below is affected by the power of the lens on the chuck. This slide shows the transmitted Bessel beam as seen by the PSM. The PSM has its focus at the height of the center of curvature of the meniscus element of the doublet, as sitting on the vacuum chuck. On the left, no lens was between the axicon grating and the PSM. In the middle, the meniscus was sitting on the chuck. On the right, the cemented doublet was sitting on the chuck. The PSM was not moved between the pictures. The only effect on the Bessel beam is to change the spacing of the rings around the core depending on the power of the lens. This is the optical design of the lens being cemented. It is a typical, fairly fast doublet with an EFL of about 50 millimeters and a 22.8 millimeter diameter. These data were used to calculate the conjugates for possible use in centering the doublet, shown on the next slide. These are 4 possible conjugates for use in centering the cemented doublet. In every case, they are at the height of the center of curvature of the meniscus. Having to move the PSM along the stage would change the alignment of the PSM relative to the Bessel beam due to a lack of straightness of the stage. This is the second advantage of the Bessel beam. Not only does it propagate in a straight line, it is detectable at any height above the lens, as if it were a simulated ray in a lens design program. When the positive element is inserted onto the meniscus, the PSM focus is 14.23 millimeters above the upper surface. A beam deviation of 1 micron is 15 arc seconds, or a doublet wedge of 19 seconds. This amounts to an edge thickness difference of 8 microns as measured with an indicator on a precision rotary table. The advantage of this method of centering, however, is that nothing had to move during the centering. This is a photo of the hardware used for cementing the doublet. The PSM is mounted on a vertical stage, centered over the vacuum chuck used as a seat for the meniscus. Under the chuck is a plain window to protect the Axicon grating and support the chuck. The grating, a fold mirror, and the single-mode optical fiber point source are all under the breadboard work table. Before showing the video of the centering process, let me walk through the process schematically so you understand better what you see in the video. The very first step is pretty much what you saw in the last slide, where the PSM is aligned roughly to the Axicon grating and the point source below the grating. Then the meniscus is set on the chuck and roughly centered using the transmitted Bessel beam so that the meniscus will be reasonably well centered as we bring the PSM down to the center of curvature of the concave side. Once the center of curvature is located, the PSM is left at that height for the remainder of all centering, and the meniscus is removed from the chuck. At this point, we do a careful centering of the PSM to the Axicon grating and then adjust the source under the grating to also be well centered. Finally, the meniscus is replaced on the chuck, and a combination of the transmitted beam and the reflection from the center of curvature of the meniscus are used to both center the chuck and the tilt in the meniscus as it rides on the chuck seat. When both the reflection from the center of curvature and the transmitted beam are centered on the PSM crosshair, we know the meniscus is centered both in tilt and decenter. Before showing the video of the setup stage of centering, I will walk you through the process schematically. The first step is as we saw in the previous slide. The PSM and source under the grating are roughly centered. Then the meniscus is set on the chuck, and the transmitted beam is used to roughly center the meniscus, so the center of curvature will be in the field of view as the PSM is lowered to the center of curvature of the meniscus side. The PSM is left at the height of the center of curvature for the entire rest of the cementing process. Height-wise, the PSM is never moved again. After removing the meniscus, the PSM and source under the grating are carefully centered on the PSM crosshair. Finally, the meniscus is replaced on the seat. The seat is centered and the meniscus tilted on the seat to make both the reflected spot from the center of curvature and the transmitted beam both lie on the PSM crosshair. When both spots are centered on the crosshair, the chuck is centered and the meniscus free of tilt. The chuck is secured by vacuum and the meniscus is ready to receive the positive element of the doublet. This concludes the setup process and we are ready for production doublet cementing. The meniscus is set on the chuck and gently slid into alignment using the transmitted Bessel beam. As soon as the reflection from the center of curvature enters the field of view, the relative brightness of it dims the Bessel beam. As seen in the last slide, the spot from the center of curvature and the spot from the transmitted Bessel beam move in opposite directions as the lens is either tilted or decentered. This graph shows the spot motion due to tilting the lens in the chuck for the case where the chuck is decentered by 50 microns. The reflected spot from the center of curvature moves about 3 times as fast as the transmitted spot. While the spots can be made to coincide at about 052 degrees, they cannot be made to lie on the center of the crosshair until the chuck is fully centered. The advantage of this is that the meniscus is used as part of the centering of the chuck. If at any time the spots do not coincide at the center of the crosshair, it is clear that the chuck has been decentered. All it takes to restore centration is to repeat this step of the setup process to recenter the chuck. To finish the centering, we need to center the chuck as well as the meniscus. After overshooting, we go back to tapping the lens to correct the tilt. There's still a little misalignment, so we decenter the chuck again. Then, with a little more gentle tapping, we bring the combination of chuck and meniscus lens into near perfect centering in tilt and decenter. At this point, we increase the vacuum on the chuck to hold it centered for all further operations. The centration is good to 2 microns in X and slightly over 1 in Y. I will leave it at that since this is a demo of the process and not of my skill. A 2 micron error at the 20 microns above the lens amounts to about 10 seconds of arc angular error in reflection. From the previous slide and the left-hand schematic picture, the meniscus is now centered, ready to receive the positive element. Once the positive element is in place, the PSM is no longer at a conjugate of the doublet. We have to rely on the transmitted Bessel beam to align the combination of elements. After adding a drop of cement, the positive element is slid onto the meniscus. The Bessel beam rings indicate the direction to move the element to center it. Once the core is visible, it is easy to tap the element into place. At the end of the process, the spot was submicron in both directions, and the cement is ready for curing. At the roughly 14 millimeters above the lens, a 1 micron error amounts to a 15-second wedge error in the doublet, or about 3 microns edge thickness difference. Once the chuck is centered, the setup is finished, and none of the hardware needs to be moved again unless it is accidentally misaligned. As the next slide shows, one meniscus after another can be centered on the chuck and clamped with vacuum, ready to receive the positive element. A previous slide showed the positive element alignment was almost trivial. When the cement is partially cured, the doublet is removed and the chuck is ready for the next meniscus. The only obvious precaution is to make sure the chuck is kept clean of cement from the previous assembly. This slide is to remind you how relatively quick and simple it is to go from centering one doublet to the next. One lens is removed from the chuck and replaced by another meniscus. The meniscus is centered and the positive element added and centered, although I do not show this for brevity. Then the doublet is removed and a new meniscus added to the chuck without ever touching the adjustments to the hardware setup. All the centering adjustments are made only to the lens elements themselves, not to the setup. The adjustments are easy to make, XY orthogonal adjustments. Further, there is good immediate hand-eye feedback from the video screen to aid the centering. As seen in the video, centering the meniscus to about a micron takes an unskilled operator about a minute, and a similar time for the positive element. In a final note, you can see the spots converge on the crosshair to indicate good centering of the meniscus. If the two spots do not converge to the center of the crosshair, as they do not quite in this video, it is a sign that the chuck is misaligned. At the same time, it's easy to touch up this alignment using the meniscus as a guide to the centering. To summarize, let me say a few words about precision and speed. A 1 micron error in the spot being centered on the crosshair is a 10 arcsecond deviation of the transmitted beam. For this lens, that amounts to about 17 seconds of wedge, or a little less than 4 microns edge thickness difference measured with an indicator on a rotary table. Greater sensitivity to centering could be had with a higher power objective. The smaller field of view is compensated by the rings around the Bessel beam to guide initial centering. In terms of speed, the talk is a little misleading because so much of the time was taken up with an explanation of the process and the setup to prepare for centering. I think a realistic conservative estimate for 1 micron error centering is about a minute per element, or 2 minutes for the assembled doublet. Thank you for taking the time to watch this presentation. If you have questions or comments, please contact me by any of the means listed below.